Okay, good afternoon everybody. I hope everyone's having a wonderful day. So before I get started with today, I just want to remind you that assignment 2 is out. It is due by the end of February 16th. Keep in mind that 8:30 rule will be in effect, so you can submit until 8:30 in the morning on the 17th, and that's perfectly fine. Note that the sample solution for assignment 1 will come out over the weekend. If not before then. It will be sometime early on the weekend. I just have to wait for a couple more submissions that are just sort of edge cases. So that being said, you will have a full sample solution you can work with until the grading is done for assignment 1, which unfortunately will sort of line up with this deadline. So I encourage you to look at the sample solution when you start playing around with assignment 2, if you find yourself wanting to say, okay, well, what does Dan expect from me? So you get some idea of the way I would approach something like this. You know, like, okay, this is a wonderful way of approaching this. Maybe I should consider doing that. Before we get started, one other detail. I was about to mention it. If you haven't done the onboarding quiz, make sure you do the onboarding quiz. Keep in mind that you're going to need to do that to complete the midterm and the final. So make sure you complete this if you get some time a little bit. So before we proceed, are there any questions? Do note that I did make a video discussing assignment 2. So it's about a half an hour long. I made sure I time-stamped it. But it is available. You just find it on the Your Courses page. You'll find it right with the assignment 2 item. If there aren't any other questions, give me 2 thumbs up if we're ready to start chatting about some fun stuff today. Awesome. I'm seeing lots of thumbs up. Awesome. This is the kind of stuff I love seeing. So anyways, we're going to talk about 2 interesting things today. That's perfectly fine. So we're going to be talking about comparison-based sorting. So we're going to conclude our discussion with lower bounds. I thought I would leave us with kind of like one of the classic results out of lower bounds. So last day I showed you how you can prove that there is a big omega n worst case lower bound for sorting. That proof made very few assumptions. However, usually it'd be nice to have a better lower bound if possible. So it gives us some better information for what our best known algorithms might be. Because most certainly, I've told you about comparison-based sorting algorithms before. We talked about it last day, right? How I told you that, oh yeah, there's like heap sort, there's merge sort, there's some versions of, well, there is a particular version of quicksort that does run in big theta nlogn time. There's a very specific pivoting strategy that allows that to happen. But you'll notice that this bound here doesn't really account for that gap, right? There's a gap that persists between this lower bound and our upper bound, right? Between n and nlogn. So you might ask, Dan, so what's the hubbub about this? Well, we would like to have a lower bound result that helps inform us for certain types of problems we might be studying if we're actually at that threshold. So for general sorting, maybe this is a nice lower bound for us. There might be some cases where that's actually going to be quite relevant. However, we've been talking a lot about comparison-based sorting. You've seen a lot of comparison-based sorting algorithms, for example. Everything from bubble sort all the way up to, say, merge sort, quick sort. These are all comparison-based sorting algorithms. So if we take on the question of dealing with the sorting problem as I posed it in the most broadest sense, meaning I have n comparable objects, can we improve this lower bound from big omega n? The answer is yes. So just before I proceed, I want to just remind you what it means for me to have comparable elements. So if I give you an array with comparable elements, you know of many different types of elements that are comparable. For example, numbers, such as integers, you can order them from smallest to largest. You know about strings if you put them in lexicographical order, for example. That is an ordering, and that allows you to compare one string against another to determine which comes before, which comes after another element. Just like I have my lovely friends over here, I've ordered these elements, these lovely characters, by their height. Note that Blue's Clues here, the dog here, is kind of cheating. He's wearing a funny hat. Doing some cooking over here. The point is that I have I'm going to have a set of elements that are comparable. Does everybody understand what I mean by comparable then? So, for example, all these elements are comparable by their heights. Just like I can have my integers, I can talk about the magnitudes of the numbers. And I could sort them from smallest to largest. Okay. So if we're okay with that, let's proceed. So I must stress, remember, I'm not going to make, so when I'm going to talk about comparison-based sorting, I'm going to make no other assumptions other than there are some set of comparable elements. That's a very important thing I want you to remember and keep in the back of your mind. It will come up a little later. So yes, we can improve the lower bound when we deal with comparison-based sorting. Now you might ask, Dan, how are we going to accomplish this? Now, we've talked about models of computation before. I'm going to talk about another model of computation. It's called the comparison-based model. And in the context we're going to use it, we're going to talk about it with respect to sorting. And the way the comparison-based model will be applicable for us is to study the number of comparisons that the algorithm is going to perform. So you might ask, okay, so Dan, what are these comparisons going to be and what's that all going to be about? Let me lay out the rules of this model. Just like, when I talked about the RAM model, I gave you some rules for how we measured the complexity, right? I'm going to do the exact same thing here, and I'm hoping maybe within the next 5 to 10 minutes, I'm going to be able to convince you that this model corresponds to the model that you're familiar with for a computer, at least in this confined setting. So this comparison-based model is going to be suitable when I have an array of n distinct elements. Now I must stress that the proofs and the techniques I'm going to show you, they can be easily adopted where they're not distinct. It just makes it easier for me to prove the claims when I make them all unique from each other. So I'm going to give them names x1, x2, all the way up to xn, and they can be compared, so they're comparable. Now like I said, there's going to be no other assumptions made about the elements. So there's nothing I can do with these elements other than compare them. So it means that one element comes before another, or one element comes after. For example, if I'm dealing with numbers, you might ask, like, does this element come before this element? By asking questions, is x less than y? For example, if these were two elements in the array. So this is, for example, a comparison. It's asking, does x come before y? So that brings me to talking about kind of the big rule here, is that if I give you two elements in the array, a comparison has the following form. It's a question. I ask if xi is less than xj, just like I did right here. The answer to this question is either yes or no, and we measure this as one comparison. So the measurement of one comparison is every time I ask a question like this, that's one comparison. Now here's where it's going to sound a little bit, I don't know, magical in some way. But keep in mind that it's not really magic. It's just that I'm measuring the number of comparisons. So there's some things I'm not actually going to measure in this model. So here's another fact I'm going to presume about any algorithm that's going to fit in this model, is that the algorithm can reorder the elements. So at any stage, it could reorder all the elements. And it's going to be done at no cost of a comparison. So your algorithm is allowed to shuffle around elements, for example. Say if I give you an algorithm like insertion sort, you know how insertion sort will take all the elements and maybe shuffle them all over by one, for example. That costs nothing. Likewise, one other thing I'm going to presume is that the algorithm has to output a permutation of the input. So if I give you elements x1, x2, all the way up to xn, it's got to give me some ordering of x1 through xn rearranged so that they're sorted. And you're quite used to this. When we sort our arrays, we would like to have them so that when I give you the array, all the elements are sorted in the array. So this shouldn't be something too radical, right? So I have some array, I do comparisons, And whenever I make a comparison, it costs one comparison. And that comparison is just a question. Does this element come before the other element? So are there any questions about kind of the general setup? So I will be telling you how the model computes things in a moment. And I'm hoping I'll be able to convince you that there's some way to translate this into a computer program. So here's one question I do have for you, and this is more of an exercise. Every one of the comparison-based sorting algorithms you're familiar with, like bubble sort, insertion sort, selection sort, say for example, quick sort, merge sort, heap sort would also be thrown in there too. Convince yourself that every single one of those algorithms can follow these rules. So if I were to give you, say merge sort, for example. Okay, I get an array. A merge sort always it makes comparisons based on the magnitudes or whatever one element comes before another, right? Merge sort may rearrange elements, and it outputs some permutation of the input, which it does. It outputs a sorted array, right? So do you see how different sorting algorithms if they're comparison-based, they all fit the rules of this model, right? So I'll let you think about that and convince yourself of this fact. It's a very interesting thing. So anyways, I got to tell you how this model actually processes, because I haven't really told you anything other than these are the rules for how we're going to do our analysis, and these are just kind of the general setup for the comparison-based model. So is it okay if I head over this way? Just want to make sure, because I know I have a lot of writing here. Okay, so I'm going to proceed over here. I'm going to show you a fun picture. So, you might ask, how do we process things with the comparison-based model? And now, it all comes back to trees. You may have seen trees before. You may have seen, for example, binary trees. And it actually all boils down for the processing of these comparisons, because remember, the comparison-based model performs comparisons, right? And anywhere in between, it can reorder the elements. That's just something you get for free in this model. So, how does it work? It's actually a decision tree. Now, if you've never seen a decision tree before, it works as follows. You have the internal nodes being comparisons or questions you might have, and the children are going to represent decisions you can possibly make. For example, in our case, we had either the answer yes or no. And in our model, when we are adapting this decision tree idea, they call it a decision tree, of course, because it's based on decisions we make. And it's a tree. It's very natural. That's one thing that's really great about a lot of this terminology, is that most of the time it just spells itself out with the way they name things. So if I have the leaf nodes, these leaf nodes are going to be labeled with the output. So it'll tell me some permutation of the elements such that they're sorted. So when I have my computations that are going to happen with my sorting algorithm, depending on what the input looks like, it's going to ask a series of comparison-based questions, right? It's just going to ask, is this element less than that element, right? So if I give you any one sorting algorithm, given some input, it's going to have a corresponding so-called decision tree that might look something like this, for example. It doesn't have to look like this, by the way. It may ask these questions in a different order, for example. So suppose I give you 3 elements, for example. One such decision tree might look something like this. So I might first start off, say my sorting algorithm under this model, say it first asks if x1 is less than x2. Now, keep in mind, the algorithm can always reorder elements anywhere in between any of these steps, any of these questions. But it gets that for free. We're going to count the decisions we make. So we can either say, yes, x1 is less than x2, meaning that we would proceed to this child of that node there in the tree. And then we can proceed to ask, is x2 less than x3? If it's yes, then we know, then we can find out right away that it's sorted in this manner. You can think of it like I'm posing you a bunch of questions and I ask you, is it sorted or not based on my input? So this actually gives you a way to pose a series of questions of yeses and nos so that when you reach a leaf, it tells you what order they should be in. So notice that every question, remember, is a comparison. So notice that x1 is less than x2, that's a comparison. x2 is less than x3, that's a comparison. And I must stress again that for any, so if I give you some array of length, say there was like 3 elements again, and I give you a different sorting algorithm. And now keep in mind, this is just a picture just to show you the idea, but conceivably you could go to any one of the sorting algorithms I mentioned earlier. You could draw out one of these decision trees based on the order it performs the comparisons. And keep in mind, if you use this, depending on what x1, x2, and x3 are, depending on what their values are, you can navigate this tree to determine if x1 is less than x2 and x2 is less than x3, or any other ordering that may take on. So I have a question for you. If you look at this tree, there's 2 things I really want you to observe about this tree. So the fun thing about this lecture is I get to kind of come back to talking about properties of trees. So that's one thing I get very excited about. So think about it. If I were to conceivably have some algorithm that does some sorting process, just hypothetically speaking, if I wanted to have the execution of my algorithm, what does that correspond to in this tree? So if I were to execute, say, given x1, x2, and x3, I don't know what their values are. Say that's just some input. And suppose this is the decision tree that you get from your sorting algorithm. What would the execution given x1, x2, and x3? I don't know what they are. They're just some part of, that's the input. They may take on numbers, for example. They could be strings. The point is what would correspond to the execution of the algorithm in my decision tree? Anybody have any ideas? So I'll tell you, there's a very natural correspondence between what this tree does and what your algorithms that you're familiar with would do. So I'll give you a hint. Remember about these leaf nodes. Those are the ones that tell you what to output. Are there any ideas? Any ideas at all? Don't be shy. What's the question? What would so suppose I gave you some sorting algorithm and say this was the decision tree for if I have 3 elements. I don't know what their values are, but if I were to execute that sorting algorithm, what would that correspond to with my decision tree here? So I'll give you a tip. The leaf nodes tell you the output. So think about it as, remember, the comparison-based model is a model of computation. So it's going to have a correspondence with something that's going to happen if we were to run this on, say your sorting algorithm on a computer. So that I haven't quite got to talking about how many leaf nodes there are, but think about it. Suppose I gave you x1, x2, and x3, and say, in fact, x1 is less than x2 is less than x3. If my sorting algorithm first checks x1 is less than x2, it goes this way because x1 is less than x2, right? I ask, is x2 less than x3? In our example, yes. And in my decision tree here, it says, hey, look, x1 is less than x2 is less than x3, and I'm done. So are there any ideas what that might correspond to in a tree? So remember, every time I answer yes, no questions until I get down to a leaf. What would this correspond to? Think of it in terms of a sorting algorithm, and suppose this was the decision tree that sorting algorithm was doing. Now, those comparisons, so I have a suggestion about comparisons. So remember, the sorting algorithm, like I tried to convince you earlier, all of them perform comparisons. They're going to correspond to this tree. The question is, what does the execution of the algorithm correspond to in relation to this tree? So I'll give you another hint. Where the program would start is sitting right at the root. I know this is a little bit something to think about, but once you see it, so I'm not referring to iterations because there are no iterations here in this tree. I'm asking what in the tree corresponds to the execution of the sorting algorithm. So just remember the rules of the model. It performs comparisons. It may shuffle around or rearrange elements, but those are not reflected in the tree. So very close. It's involving branching. It involves the branching. So the question is, there's a name we give that. The path. The path. That's what I'm looking at for. The execution corresponds to the path. It's a path. From the root to a leaf. Very good. Very good. So, if the execution refers to that, I have another question for you. So remember, all of the comparisons form this tree, meaning that all possible executions of given x1, x2, and x3, this entire tree represents all possible ways that the comparisons can occur over x1, x2, and x3. I just don't know what their values are, so I can compare them. So the natural question I have for you, so there's another question. So if I give you my sorting algorithm, what is the maximum the number of comparisons required in the worst case? So we already established that the execution of the sorting algorithm corresponds to a path. So we know one execution of the algorithm is a path. So how do I figure out the number of comparisons made in the worst case? So I'm not looking for a big O. I'm looking for what structure in this tree would that correspond to. If I tell you one execution of the program is in fact a path. So would, for example, the worst case correspond to, say, this leaf here? Or would it be one down here? So yes, it will depend on the execution of the algorithm, indeed. But remember, we're thinking about this in terms of worst case. So yes, so I'm seeing some numbers about how many, but the question is, okay, if one execution, as pointed out, is going to end up being one of these paths, then most certainly the worst case has to be the longest path in the tree. So that is the maximum depth of the tree. So this refers to the longest path, which this isn't just simply going to be that the worst case running time, is at least the depth of the whole tree. Is at least the depth of the tree. So if I look at one sorting algorithm, that sorting algorithm will have a corresponding decision tree. I execute one given input, it will correspond to a path in this tree. In the worst case, it will correspond to the longest path. So your worst case scenarios will end up being these longest paths. And that means that the worst case running time is at least the depth of its corresponding decision tree, right? And each sorting algorithm will have its own decision tree. So we're going to use this fact to help us establish a lower bound. So everybody got the general gist of the idea. So I'm going to try to find some relationship between the leaves of this tree and the height of this tree so that I can try to figure out some way I can get a lower bound on the depth of the entire decision tree, regardless of which sorting algorithm you pick, because each comparison-based sorting algorithm you pick, because each one will have its own decision tree. So that's going to be kind of our game plan here. So is everybody okay with that? So just remember, this model here is just another way of thinking about the computations. Just we're measuring the comparisons. So if we're okay with this, I'm going to proceed. So let me proceed over this way. So just keep in mind, the worst case running time is at least the depth of its decision tree. That's the big thing I want you to keep in the back of your mind. And remember, we're trying to establish a lower bound in the worst case. And I've seen some interesting things brought up in the chat there, actually, we're going to probably take advantage of. So I see that some people were thinking a little bit ahead of where I wanted to be. So this is wonderful. So here's the theorem. For the sorting problem, on an array L of n distinct elements, any comparison-based sorting algorithm, must perform big omega n log n comparisons in the worst case. And I must stress that this theorem is just as applicable if it's a deterministic algorithm, in the sense that all these comparisons all have a predefined ordering, but also in the case when it is so-called a randomized algorithm. But I'm only going to prove it in the case of being a deterministic algorithm. I mean, there's no randomized coin flipping or anything like that. But the proof is quite similar. You could also establish a lower bound just like this one in the average case too. So when I talked about n log n in the average case, so for like merge sort, quick sort, for example, runs n log n in the average case, that lower bound also is established. And the proof is actually quite similar to this one as well. It's not the same, but it's similar. So here's the idea. And most of this proof, believe it or not, is just about invoking properties of trees. Some of them you've seen before, which is really kind of fun in its own regard. So it's almost like I get to do a review of trees with you. So the proof is going to begin by me just saying consider any, and I'm going to implicitly assume it's a deterministic algorithm, any comparison-based sorting algorithm, A. So I'm going to call it A, observe that in its decision tree, there's kind of two things that we're going to use as key ingredients. Then once we observe these two ingredients, we almost are there, which is, it's actually kind of funny in its own regard. And I've seen actually somebody bring up this property actually in the chat, which is wonderful. So the number of permutations of L is, and I've seen it in the chat. Can somebody tell me how many permutations are there of the input? I seen it in the chat earlier. So if the length of the array is n, then yes, it's n factorial. Perfect. But what does this correspond to? Each permutation is sitting as a leaf in that tree, right? If you examine the tree, every one of the leaf nodes is one such rearrangement of the input, which is the number of leaves in the decision tree. So that's our first fact. This one's not too bad. It's some basic counting. Okay, I have a question for you. What was the shape of our tree? Is this like a tree with many, many children? We have a special name for the kind of tree that decision tree is. It starts with a B. It's binary. It's binary, exactly. So we have very nice properties when we're dealing with a binary tree. So observe that the decision tree is binary. Means it has, my apologies, I'm getting very excited here. I maybe hyped myself up a little too much. Observe that the decision tree is binary, and a binary tree with height h has, I'm just going to drink some water. My apologies. While I'm drinking some water, can somebody tell me how many, what's an upper bound on the number of leaves of a binary tree of height h? Ah, there we go. Much better. Much better. I'm just getting really hyped here. With height h has at most, well, think about it. Just going to kind of do a little doodle off to the side. So a binary tree with as many leaves as possible, we'll probably put them all at the bottom level of the tree. Sorry, I'm just having a little bit of I'm having a moment, everybody. Well, the question is, if the height is, for example, h, what's an upper bound on the number of leaves? So notice that it always goes up by powers of 2, right? So it's going to be at most 2 to the power of h leaves. So I'm just going to take these two things and I'm going to just slam them together to derive a nice result for us. The maximum number of comparisons made by A is the height h of its decision tree. So once you have this fact, all we have to do is just spell out one interesting connection between these two facts I just gave you. And the number of comparisons, actually, instead of saying and the number of comparisons, I'm just going to cut it here, and then I'm just going to say and. So let's just going to cut this a little bit shorter. And remember, 2 to the power of h is an upper bound on the number of leaves, right? So I can write this. I can say 2 to the power of h is greater than or equal to n factorial, right? Because 2 to the power of h is an upper bound on the number of leaves, and the number of leaves is n factorial, right? Now watch this. I'm going to try to get h. So my goal is to get this h, because remember, h is going to tell me the number of comparisons made in the worst case, right? So what I'm going to do is I'm just going to apply logarithms to both sides of the inequality. So this is true if and only if h times log base 2 of 2 is greater or equal to log base 2 of n factorial. So I'm just applying logarithms to both sides, and then I apply the power rule of logarithms. What's log base 2 of 2, everybody? What's log base 2 of 2? I see in the chat, it's 1. So this right here is just 1. So what does that mean? It means we could just simply say that h is greater than or equal to log base 2 of n factorial. Now you might ask, Dan, what do we do with it after this point? Well, there's a little bit of nice and analytical tricks you could do. And you could break this down a little further to establish that this is big omega of n log n. Now, I'm going to leave those details for you to look at in the notes just for the purposes of time here. I would otherwise go through it all with you. But I wanted to start talking about our next subject, but I need to wrap up this proof here. So notice that the number of comparisons made is now, so note that the way we obtained this log base 2 of n factorial, it's actually through a little bit of neat bounding techniques. But I'll let you take a look at the details for this step here. Take a look in the notes for the details of how you derive this. It's a very neat technique, so I encourage you to take a look at it. But yeah, so you might ask, so Dan, what does that mean for us? Well, I promised you I was going to show you how merge sort, heap sort, and all of these were in fact the best known comparison-based sorting algorithms, among some others, that we know of. And this theorem demonstrates that, because it establishes a lower bound for comparison-based sorting. So the natural question you have is, okay, so wonderful, wonderful. So what do you do with this? So before I proceed, are there any questions about the argument I presented here? Does this seem okay? So like I said, I want you to take a look in the notes to see what happens in this step here. I don't see any questions, so I want to talk a little bit about the consequences of this and what it says and what it doesn't say. So let's boogie on over here. Because that seems like a rather interesting lower bound result, right? So, what does it mean? So, I'm going to say that we have big theta n log n time comparison based sorting algorithms. Just as examples, we talked about merge sort briefly. I'll tell you that these are optimal sorting algorithms. With respect to time complexity. So why do I say this? So when I mean optimal, I mean that the upper bound for time complexity for solving the problem meets the lower bound. Since I have for an upper bound my big theta n log n for comparison-based sorting, and I established that lower bound of n log n for comparison-based sorting, that means that comparison-based sorting, as far as asymptotic time complexities and so on are concerned, this is the best you're going to accomplish. Now, beyond that stage, you might start asking yourself some other questions. So, what exactly can you do beyond that? Well, first, there's the practical considerations. So, for example, when you pick up a sorting algorithm, you may further try to optimize based on your inputs. But most certainly, we're still studying kind of a very broad class of problems. Remember, the input in this sorting problem is any comparable objects, which is a very, very, very broad. So I must stress that lower bounds are an invitation. So don't look at the lower bound as an end of the story. I like to think of it like an invitation. Because the lower bound, yes, for comparison-based sorting, it tells you, hey, look, this is probably going to be the best you're going to accomplish, period. But it's also an invitation, because if you're studying sorting, for example, you may not necessarily have it where they're always just going to be n comparable objects, right? So just remember, we made very few assumptions with more assumptions our result may not hold. Because remember, I'm thinking of like the broadest classes of sorting. So you might say, okay, so with more assumptions, and keep in mind, these also could be practical considerations, right? So for example, if I know my input is always a set of integers, there's actually more you can do with sorting. But I'll give you an example of what I mean, just before I get to talking briefly about that. Suppose each element xi is either 1 or 2. So this is saying xi is 1 or 2. It's 1 or 2. So suppose each element is of this form. Can you think of an algorithm that runs in little o of n log n time? Now remember, our comparison-based sorting algorithms will work and solve this instance. But suppose I give you an array where each one of the elements is either 1 or 2. Is there anything you could do that's faster than n log n? Does anybody have any ideas? Any ideas at all? Suppose the array just has 1s and 2s in it. That's it. Is there anything you could do to design a more efficient algorithm in this case? Any ideas at all? So I'll draw a picture to help us kind of talk about this. Suppose I have like 1, 2, 1, 1, 2. Say, suppose that's the array. Any ideas at all? Remember, there's only 2 different kinds of elements here. There's either 1s or 2s. That's a big hint I'm giving you. And you know the 1s always come before the 2s. So can you think of an algorithm that takes time less than n log n to accomplish this in the worst case? So, I'm not seeing any takers. Go on, don't be shy about this. Believe it or not, this problem is actually much easier than you may think it is. So for example, here's an idea. So count all the 1s. Then place all 1s to that part of the array. So for example, notice that if I scan from left to right, I can count how many 1s there are. I know all the other elements are 2s, right? Yes, so that's another good suggestion, is whenever we see a 2, we just put it at the end. But now, the question is how you put it at the end. That's where things get a little bit tricky. So all I'm going to do is I just scan from left to right, I count how many 1s there are. And then all I do is I write how many 1s there are based on the count. And then you have all the rest of the array filled up with 2s. And you can accomplish this in linear time. So you can do this in big O of n time. So I'll let you look at the notes for more details about this. But the point is that you could just simply go through them from left to right. Okay, gotcha. Yeah, no, so just remember, we're talking about problems like we talked about at the beginning of this class, the first lecture. So remember, each one of the elements in this case was just a special case where all the elements are 1 and 2. That's it. So notice that, that here you can do much better. So that lower bound result actually is inapplicable to this case because it's much, much more specialized. So the lower bound doesn't say things about these cases. Just like there are other types of sorting problems you can also encounter. For example, there also exist so-called non-comparison based sorting algorithms. For when the input is integers, for integers. When you assume that the number of bits for the number is constant. So, and this is typical when you're dealing with practical situations, because if you have all your if your array consists of integers, all of them have a fixed number of bits, correct? So there do exist things called non-comparison based sorting algorithms. For example, they often will bucket based on this counting idea I just presented to you. So what you do is you bucket the elements based on how many discrete entities could exist because you know how many representations could exist. But there's several of these kinds of algorithms. For example, in this circumstance, you can use something it's called radix sort. Radix sort. And these take big theta n time. So if you're dealing with integers and those integers are small, you can use, for example, radix sort to accomplish this in linear time. But the big point here is that this is dealing with a special case of our problem, right? Remember, our problem is given n comparable elements, sort it. But these are much more specialized situations. So these are two examples, and you could look at these like invitations. So if you're wanting to solve the much more general sorting problem, these lower bounds hold. However, if you're specializing, remember, think of it just like a special case of the problem, some subset of those instances. Those can actually be attacked and you could come up with more efficient algorithms in some circumstances. Sometimes lower bounds hold in those cases too, but most certainly in these two, for example, you could come up with much faster algorithms. So that's all I have to say about lower bounds. So are there any questions before we proceed to our next topic? So this is kind of like me going as deep as I can into lower bounds. We're going to kind of come back up to the surface again. So if you feel like there's a lot of stuff going on, it's going to lighten up again. Do another example. So for what do you mean by another example? Just to clarify. Just want to make sure I'm not saying something I might not be. If there are different x values in the array. Okay. So so keep in mind that the same strategy I used here, where I had xi's being 1 and 2. So if I have xi being 1 and 2, the principle behind this sorting algorithm is simply I bucket all of the ones that belong to the 1s together, and then I know all the other ones have to be 2s. So if I have this one, I can easily just rewrite this as 1, 1, 1, 2, 2. But I must stress that this example is a very big rabbit hole. I just want to make sure that you're aware that linear time sorting algorithms do exist. They just rely on more assumptions. For example, if you know that the integers, say if you're dealing with integers, you have some constant number of bits. But think of this as an invitation. If you have some problem you're studying, consider if you're actually studying this much more general problem or some special cases like these. But yeah, so anyways, I'm going to have to shift over to the next topic. So hopefully you'll appreciate that this is a little bit of extra explanation about this. So let's proceed this way, because the next topic's really important for the next assignment. You're going to be playing around with this idea for the next for a little while. So we're going to start talking about it. Then we might finish it up next time. So let's just proceed. So we're going to be moving into the next part of this course. So we're going to start talking about data structures. So that's the end of kind of the big kind of overview of algorithm analysis. And I want to shift gears to now talk a bit more about analysis and different data structures. So we're going to move into the next part involving data structures. So this would be kind of like the advanced data structures part of this course. So the first thing I'm going to do is I really want to really emphasize that we're going to start looking at data structures that are beyond the ones that you've seen in 210. So you're going to notice that I'm not going to touch upon a lot of data structures you've seen in 210, but sometimes you'll see some cross-pollination of ideas you've seen from 210. So sometimes it'll just be like, okay, that sounds kind of familiar. It's by design. So the first topic I want to talk about, which it'll feel like I haven't really moved out of the previous topic so much, but it's highly applicable to data structures, So I want to give you an introduction to amortized analysis. So I'm going to first start off by trying to motivate why we might need a little bit better of an analysis technique for sometimes when we're dealing with data structures. So often, classic worst case analysis may not capture a more realistic scenario where faster, inexpensive operations occur very often. But the worst case, happens infrequently. It happens infrequently. And this happens all the time, believe it or not, with a lot of your data structures that you've seen previously. They oftentimes, let me give you some examples, just to make sure I'm very clear about what I mean by this. So you may have heard of, so if I have a dictionary, for example, or a stack, for example, or a queue, keep in mind they all have different names for their operations. I'm just going to stick to a dictionary, just to keep things simple, or a map. Some people call a dictionary a map. The put or insert operation of an array-based dictionary. An array-based dictionary. So of an array-based dictionary. Or the push operation of an array-based stack. So in both of these circumstances, if I'm using an array to represent, say, for example, a dictionary, or some would call a map, or say if I'm using an array to represent a stack, in both of these circumstances, you run into one case that happens that causes the time complexity to run in linear of the number of items that are in your collection. Can anybody point out that worst case situation in here? So if I have doing insert operations for, say, a dictionary or a stack, these are obviously two different data structures, but they have the very similar flavor to what happens when you're dealing with an array-based implementation of them. So if you do a bunch of insertions, okay, well, maybe we'll start with we'll go one step back. If I'm doing an insertion and there's room in the array, what happens? I could just put it right into the next available spot. Maybe I have a variable that tells me where the next free spot is in the array, and we insert it in, right? This happens almost all the time, right? That's typically how we try to do this, is we try to make the array big enough so we can fit all the data that we need in. However, it's still, there's this worst case scenario that happens. Could somebody tell me what happens in the other situation than the one I gave? So if I have my array, I would like to be able to insert the next element into the array. So for example, if this is a stack, it would be like the next position that's free, but it's the one furthest to the right, but not any further than all the occupied spaces in the array. I put that in. But what happened? So what case causes worst case behavior here? So keep in mind, every time I do, for example, a push operation in an array-based stack, it's usually very, very fast, right? You can do it in constant time almost all the time, except for one situation. There's one very specific time in an array-based stack where you're going to run into a problem. Yes, it's when the array is full. So when the array is full, this is one of those expensive operations that doesn't happen very often, but it's indeed the worst case scenario, right? So in those cases, you have to allocate yourself a new array, copy all of the contents of your array-based stack into this new larger array, and then you can insert in your element. So in this case, if you're doing the push operation, you're putting the new element that's going to be at the top of your stack. If it's a dictionary, this would be wherever it's supposed to go, but most certainly you have room to place it in. But yeah, both of these situations have the same effect, is that when I have an array, it's possible that it becomes full, and I have to allocate a new array that becomes my new resized array. So we're going to see an example just like this one when we start looking at doing a more thorough analysis. Another example that you most certainly will run into, if not you've seen it before, is if you ever use a hash table. So here's another example. So if I have a hash table, now, what happens when you run out of space in your hash table? So if you have a hash table, what happens when you have no more space to put things into your hash table? What do you have to do? I'll give you a hint, it's very similar to the previous circumstance. So if you insert elements into your, so you put some more things, yeah, so you have to allocate more space, correct? So we have to allocate more space, but you have to rehash the entire table to your bigger array, correct? So in this case, when we rehash the table. So both of these have a very similar phenomenon going on, where almost all the time you're going to have these fast and expensive operations, but the worst case, like there is a worst case that happens, it's possible that the phenomena that we just described can occur. But the problem is that in most realistic scenarios, you're not going to run into that unless, and it happens sort of in a delayed manner. So it's something that doesn't just happen every time. It happens only when you run out of space with your array, for example, in both of these circumstances. Likewise, so does everybody get the general idea of what we're trying to talk about here? Is that worst case analysis is way too pessimistic. Like worst case, okay, it is a pessimistic type of analysis, but maybe it's too pessimistic when we start talking about data structures. Because when we do operations with data structures, it isn't just that we do one operation, right? We usually have a sequence of operations that we do so that we can modify the data structure. So that's what amortized analysis is going to help us address. So does everybody understand kind of like the big game plan here? So if this is okay, give me 2 thumbs up. Okay, wonderful, wonderful. So the big thing here is worst case, maybe too pessimistic. Maybe too pessimistic. So, what are we going to do then? Well, like I said, amortized analysis is for considering a sequence of operations a sequence of operations as opposed to a single one. I'm losing my friends. They're falling down. So we're going to consider, we consider worst case, so we're going to consider worst case running time per operation. So that's what amortized analysis is we're going to consider worst case running time per operation. So I'm going to give you some sequence of operations, and I want to develop a general form for counting the number of operations that occur for any one operation. And I want to compute the worst case running time per operation. Because surely if many, many inexpensive operations happen, I would like to know if that happens more often than that nasty worst case, right? So you could look at this like I'm looking at the worst case on average, if you think about it like that. Another way you could think about it is it gives you an idea if I have a whole bunch of operations that are going to happen that mutate my data structure. Then what it does is it also tells me, like if I have many operations that happen, what should I generally see when I do several operations? Is it going to be very cheap to perform it? Or if I add up all those operations that happen as per the amortized, what we're going to call the amortized complexity, if I add up all those operations, it will actually give me the worst case running time. So if I have n operations that happen, if I have the amortized complexity, which we'll talk about in a moment, then it will tell me actually the worst case running time overall. So it's actually useful in two ways. One, it gives me some insight of what is happening with these inexpensive operations versus the ones that are expensive. But it also allows me to actually compute worst case running times of a sequence of operations. So for example, if I have, say, a stack, and I perform n pushes on this stack, I want to know what the time complexity of pushing n elements onto the stack is. The amortized complexity can tell me that by just simply taking the amortized complexity, which we'll define in a moment, and multiplying it by the number of operations you do. You can think of it just like basic measurements. So this is worst case per operation as opposed to just worst case. So let's proceed over there. Let's talk a little bit about this before we wrap things up. So what we're going to explore for the main phenomenon we're going to look at, which captures pretty much both of these cases that I had. Well, actually, all of those cases I described. I'm going to provide you a rather general pattern for doing amortized analysis. To explore the concept, that R sort of just melted. To explore... Oh, but thank you. Thank you. Let me fix that right now. Excellent. Thank you so much. You caught it for me this time. Thank you. Thank you. To explore the concept, we will consider dynamic arrays, which sometimes these are called resizable arrays. And you may actually be familiar with these, you may or may not be. For example, in something like C++, you may be familiar with the vector, like the vectors. These are examples of dynamic arrays. So whenever you run out of space, it allocates more space so you can perform more of your operations on, say, for example, a list, for example. So this is going to be the primary data structure we'll play around with when we talk about this. I want to do an example just to kind of give you a flavor for what I mean by worst case running time per operation. When we come back next time, I'll define what the main method we're going to use for amortized analysis. It's going to be the aggregate method. But I want to show you just the idea behind this, just before we get too cozy here. So suppose I give you a sorted dictionary. So this is just warm up. This is more of a quick analysis. I'm going to go way more thorough next time. So we're going to consider a sequence. Consider a sequence of n+1 put or insert operations into an array, of length n. Now, before I get too ahead of myself, to perform an insert into a sorted dictionary, what this would need to require, at least for what I'm going to be doing, because I'm going to assume that this is a sorted array, to perform the insertion into my dictionary, which will just contain keys and values, or keys and data, to do this, I'm going to have to maintain a sorted array. To accomplish this with an insertion, I'm going to require a linear number of operations to do this. So insert or put takes big O of n time. Now the way this works is that you perform the insertion and then it shuffles over any elements for which those that come after it. So you just go scan from left to right, you find the spot for which the element, or the record in this case, would be inserted in, and then you just simply shuffle all the other elements to the right. If there's room in the array, you could do this without having to resize it. So this takes big O of n time. So this is true for the first n operations, right? That there's always room in the array to accomplish this without having to do any resizing, right? So let me just, however, let me just wrap this up. However, for operation n+1, suppose that the array's size or length is doubled so that I can make room for more elements or records. As it is full, this still takes big O of n time. So note that every operation in my sequence, the first one, the second one, the third one, all of them are going to take big O of n, and including this nasty case, when I have to resize the array. So each operation takes big O of n time for n+1 operations. The total running time is big O of n+1 times n, which you can always simplify down to n squared if you'd like. But I'm going to keep it simple, implying put or insert has running time big O of n amortized. So remember what I said, it's the worst case per operation. N+1 operations happen. So overall, the running time was big O of n+1 times n, which you divide that by n+1, you end up with big O of n. So if you looked at this, you'd say, okay, well, it seems like every operation seems to just be like the expensive one. So this isn't very ideal if you think about it versus some other cases. So I'm going to show you next time how we can more carefully do the amortized complexity analysis. And we're going to look at an unsorted array-based implementation of a dictionary, okay? So when we come back, we'll look at the aggregate method. We'll finish up this amortized complexity discussion. So say thank you very much and have yourself a beautiful day. I'll see you later.